Welcome back to the deep end. Looking at the stack of research for today's deep dive, I have to admit, I'm feeling a little betrayed.
Betrayed. That's a strong word to start the day with.
It is, but I think it fits. We're talking about oxygen today,
Mm,
and my entire life I've been sold this very, specific narrative about oxygen.
the good guy.
The good guy. It's
Yeah.
the breath of life. It's fresh air. It's what makes my brain work. But looking at this source material, especially the work on the second states of oxygen, I feel like I've been rooming with a serial killer and didn't even know it.
It is a bit of a shock to the system, isn't it?
A huge shock.
We're absolutely conditioned to see oxygen as purely benevolent. And don't get me wrong, without it, we are dead in minutes. It's non-negotiable.
Right.
But this second phase concept is, it's vital to understanding biology. The whole premise is that oxygen is, at its core, a toxic, destructive force.
Toxic is the word that just keeps jumping out at me from these papers. And not just toxic in a, don't drink the bleach kind of way, but toxic in a fundamental, inescapable way.
That's the paradox we're exploring today. It's the paradox of oxygen. The very molecule that allows us to exist, to extract this incredible amount of energy from our food, to run marathons, to think complex thought,
To have this conversation right
to
now.
have this conversation. Exactly. That same molecule is also the one that is slowly rusting us from the inside out.
Okay, stop right there. Rusting. We use that as a metaphor for aging all the time. Oh, my knees are getting rusty. But you're saying it's not actually a metaphor?
Chemically,
Oh.
no, it is not a metaphor.
Seriously?
Think about it. Rust on a car bumper is just iron reacting with oxygen to form iron oxide.
Right.
Well, aging in your cells is, in many ways, your proteins and your lipids, your fats, reacting with oxygen to form damaged, oxidized trash. It is the exact same fundamental chemical process, oxidation. You are biologically rusting.
That is a profoundly terrifying image. I'm just picturing myself as an old car in a junkyard.
Well, we have better repair mechanisms, thankfully.
I would hope so. But if oxygen is so dangerous, if it's literally trying to burn us down, why did life ever bother with it? I mean, why didn't we just stick with what worked before? Stay anaerobic.
Because we got greedy for energy. That's the bottom line. Anaerobic life. Life without oxygen is very safe from an oxidative standpoint, but it's incredibly inefficient.
How inefficient.
You get maybe 2 units of energy out of a sugar molecule. With oxygen, you get 36. It's a game changer.
Okay, that's not a small difference.
It's the difference between a single-celled organism in the mud and a cheetah. You can't build a brain or a complex animal on fermentation alone. You need high-octane fuel. Oxygen is that fuel. But, like any high-performance fuel, it burns hot and it's dangerous to handle.
The sources bring up Joseph Priestley here. He's the guy who gets credit for discovering oxygen, back in 1774.
That's right.
And reading his notes, it's wild because it seems like he actually saw this coming. He figured it out from day one.
He was incredibly prophetic. Priestley isolated this gas, he had a funny name for it, dephlogisticated air, but we know it as oxygen.
Fishy.
Very. And naturally, being a scientist in the 1700s, he just started putting things into it to see what would happen. So he puts a candle in a jar of pure oxygen.
And of course it flared up.
It burned unbelievably bright and incredibly fast. Just poof, gone. Way faster than in normal air. Then he put a mouse in the jar.
The poor mouse.
Well, at first, the mouse was having a great time. It was running around full of vigor, seemingly supercharged by this new air.
A super mouse.
Briefly, a very briefly super mouse. But Priestley wrote this reflection that perfectly captures our topic today. He speculated that while this gas might support life, it might also, and this is his phrase, burn out the candle of life too quickly.
Wow.
He literally wondered if the animal powers would be exhausted by living in too pure a version of this air.
So even at the moment of discovery, there was this suspicion. This gives us a ton of energy, but it might be killing us faster.
Exactly. The candle that burns twice as bright burns half as long. That is the fundamental trade-off of being an oxygen-breathing creature. And our mission today is to figure out the mechanics of that trade-off. We're going to look at the strategy of attack used by what scientists call reactive oxygen species.
ROS.
Mm-hmm.
I kept seeing that acronym everywhere. ROS. It sounds like a generic corporate term, but these are the bad guys.
They're the insurgents. They are the agents of chaos inside your cells. And we really need to understand how the oxygen you're breathing right now transforms from this benign life giver into a cell destroyer.
Okay, before we get to the microscopic warfare, let's just set the stage a little with the environment. Because we aren't breathing pure oxygen, thankfully.
No, and that is a very, very good thing. We're breathing about 21% oxygen. The rest is mostly nitrogen, which is, for our purposes, inert. It doesn't react with us. It's just a filler gas.
But the sources bring up this history that I found absolutely fascinating. Oxygen wasn't always 21%. In fact, originally, it wasn't there at all.
Not at all. If you go back to the early Earth, there was essentially no free oxygen in the atmosphere. Life was entirely anaerobic.
So what changed?
These little microbes called cyanobacteria, they figured out a new trick: photosynthesis. They started using sunlight to split water, and in the process, they released oxygen as a waste product,
A waste product.
a toxic waste product. To the life forms on Earth at that time, oxygen was a deadly poison. It caused what we now call the Great Oxygenation Event, which was, very likely, the biggest mass extinction in the history of the planet.
So the arrival of oxygen was an apocalypse.
A global apocalypse. It wiped out almost everything because they simply couldn't handle the oxidation. They were rusting to death on a massive scale.
So we are basically the descendants of the few survivors who learned to wear a hazmat suit.
That is a perfect way to put it. We evolved these incredibly complex antioxidant defenses, biological hazmat suits, just to be able to tolerate this gas. But even for us, that tolerance is incredibly narrow. The notes call it a Goldilocks pressure.
Too little, you die. Too much, you die. It has to be just right.
Precisely. If you took the room you're in right now and just swapped the nitrogen for oxygen, bringing it to 100% oxygen at normal pressure, you would be in serious trouble very fast.
How fast is fast?
The source material says pure oxygen at 1 atmosphere. So, sea level pressure causes significant lung damage in about 6 hours.
6 hours. That is unbelievably fast. I always pictured oxygen toxicity as this, long-term thing that happens to deep-sea divers over years.
Well, that's chronic damage, and that does take years. But acute toxicity burns your lungs like a chemical weapon. It literally scorches the delicate surfaces of your alveoli.
And we've seen this in practice, tragically. The material highlights the case of retrolental fibroplasia in the 1950s.
Yes, this is a heartbreaking chapter in medicine.
It's awful. This was the issue with premature babies, right?
Right.
I remember reading the section and just feeling sick.
It is. You had these premature infants, struggling to breathe. Their lungs weren't fully developed. So doctors, with the absolute best intentions, put them in incubators and cranked up the oxygen.
Well, that makes sense.
It's a logical step. They thought, oxygen is good. The baby needs help breathing. Let's give them plenty of it. The more is better philosophy.
Of course.
And it worked in the sense that the babies survived the initial respiratory distress. But then a few weeks later, they started going blind.
Blind from oxygen.
Completely blind. The high levels of oxygen triggered the blood vessels in their retinas to grow wildly and uncontrollably. They scarred the inside of the eye and detached the retina. It was this devastating lesson that oxygen is a drug. And like any drug, the dose makes the poison.
Wow.
Yeah.
It really drives home the point that our relationship with this element is it's so fragile.
It is.
But then the nodes flip to the complete other extreme, these deep-sea fish.
Oh, this is the swim bladder issue. This is just wild.
Yeah, explain this to me, because if a baby goes blind from a little bit of extra oxygen, how on earth does a fish survive at the bottom of the ocean?
Well, think about the pressure down there. It's absolutely crushing. Gases get compressed.
Yeah.
Many of these deep-sea fish use pure oxygen pumped into their swim bladders to stay buoyant.
Okay.
The partial pressure of oxygen inside those bladders can be up to 2,500 times higher than what we breathe at sea level.
2,500 times. Based on what you just told me about the incubator, that fish should just spontaneously combust, or at least its cells should turn to soup.
Thermodynamics says it should be incinerated. It absolutely should. But it isn't. These fish have evolved these incredibly specialized structures. We're talking about a multi-layered wall of tissue that's basically gas-proof and massive, massive amounts of antioxidants just to keep that high-pressure oxygen contained.
A lead-lined box inside a fish.
Essentially, yes. It shows the extreme lengths life has to go to just to handle this element without dying.
Okay, so we've established that oxygen is dangerous. It burns candles. It blinds babies. It requires lead-lined fish bladders to manage. But... and here is my struggle. I'm looking at the air in this room. It seems pretty chill. I'm not on fire. The coffee table isn't burning.
And that is the chemistry of the enemy. And this is where we have to get a little technical just for a moment to understand the absolute miracle of why you are not on fire right now.
Please do. Because if oxygen is so reactive, why is there any left in the atmosphere? Why hasn't it just reacted with all the wood and metal and, well, us already?
The answer lies in quantum mechanics. It's called the spin restriction.
Spin restriction. It sounds like a DJ technique, but I have a feeling it's about electrons.
It is, and this is the single most important safety feature in all of biology. To understand it, we have to visualize the oxygen molecule, the O2 molecule.
Walk me through it.
Okay. Oxygen O2 in its natural resting state, what chemists call the ground state, is weird. It has two unpaired electrons in its outer orbit.
Unpaired electrons are usually bad news.
Right.
They're lonely, they're desperate to find a partner, they want to bond.
They are desperate to bond. That's what makes things reactive. But here is the catch, the crucial detail. These two lonely electrons have what are called parallel spins.
Okay, so I'm visualizing. Two electrons both spinning, say, clockwise.
Exactly. Now, look at the stuff you are made of. Your proteins, your fats, your carbohydrates. In almost all organic molecules, electrons come in nice, stable pairs with opposite spins, one clockwise, one counterclockwise. They're paired up, they're stable, they cancel each other out.
So I'm full of these neat little clockwise, counterclockwise pairs. And oxygen has these two rogue clockwise singles.
Right. Now, there is a fundamental rule in physics called the Pauli exclusion principle. And it basically says you cannot fit two electrons with the same spin into the same slot or orbital. It's forbidden.
So if oxygen wants to react with me,
If oxygen wants to come along and steal a nice, juicy pair of electrons from your hand to burn you, it has a big problem. It can't take a counterclockwise electron from you if it only has a clockwise slot open for it. The quantum geometry just doesn't work.
it's like trying to shake hands with someone, but you both extend your right hand and you're standing back to back. You can't connect.
That's a fantastic analogy. Or think of it like a lock and key. Oxygen is trying to react, but its key is cut wrong for most of the molecules around it. And this mismatch makes oxygen, as the source material puts it, kinetically sluggish.
Sluggish. I like sluggish. Sluggish is good. Sluggish is what's keeping me alive.
It is. It forces oxygen to be a very picky eater. It prevents it from just swallowing a whole pair of electrons at once from a stable molecule. Instead, it usually has to take them one at a time.
One at a time. That sounds like a safety valve.
It is the ultimate safety valve. It's the reason the whole atmosphere doesn't just ignite. But, and here is the massive, enormous but, that one at a time restriction is also the very thing that creates all the danger inside of us.
How is that possible?
Because when you feed oxygen just one electron, you bypass that safety lock. You create a new, unstable intermediate form. You create a free radical.
So the safety mechanism that stops the global fire is the very thing that creates the rust inside our cells.
Precisely. To use oxygen for energy, biology has to feed it electrons. But because it has to be done one by one, we inevitably create these half-reacted, unstable, angry little monsters along the way.
Let's meet these monsters. This is segment 2, the Rose Gallery. The sources list a whole lineup of them. But first, just a quick definition. What exactly is a free radical?
The simplest definition is this. A free radical is any atom or molecule that has an unpaired electron in its outer shell.
The lonely electron again.
The lonely, desperate electron. Remember, electrons hate being alone. They are obsessively driven to find a partner. So a free radical is chemically promiscuous. It will attack the nearest stable molecule, rip an electron off of it, just to satisfy its own loneliness.
Which, okay, satisfies the first radical, but it leaves the victim with an unpaired electron.
Correct. It passes the curse along. The victim becomes a new radical, and it attacks the next thing in line. It's a chain reaction. It's a chemical cascade of damage.
Okay, let's look at the lineup. Who is suspect number 1? The first one on the list.
The first one you always have to talk about is the superoxide anion. That's O2 with a little dot and a minus sign.
Superoxide. It sounds like a villain from a bad comic book. Beware superoxide.
And in a way, it is. It's what we call the primary radical. It's formed when that sluggish oxygen molecule finally accepts that first single electron. In your body, this is usually the parent of all the other reactive species we're going to talk about.
So is it the most dangerous?
Surprisingly, no. On its own, superoxide itself is, it's relatively weak chemically. It's distinct, but it's not a sledgehammer. Its real danger is that it's the precursor. It very quickly turns into much nastier things.
So it's the gateway drug of oxidative stress.
Exactly. Superoxide can react to form our next character. Now, this one technically isn't a free radical because it doesn't have an unpaired electron, but it's a major, major player. Hydrogen peroxide. H2O2.
I know this one. It's in a brown bottle in my medicine cabinet. I put it on cuts and it bubbles like crazy.
That bubbling is your body's enzymes furiously trying to break it down before it causes damage. Now, hydrogen peroxide is dangerous for a very specific reason. Unlike superoxide, which has a negative charge and gets stuck behind cell membranes,
Right.
hydrogen peroxide is neutral. It has no charge.
Why does that matter so much?
It matters because it acts like water. It can slide right through biological membranes as if they aren't even there. It can be generated in one corner of the cell, float across the room, slip right through the nuclear membrane, and cozy up right next to your DNA.
It's a ghost.
It's the Trojan horse of oxidative stress.
So superoxide is the thug on the street corner, but hydrogen peroxide is the silent assassin that sneaks into your bedroom.
A perfect analogy. And when that assassin gets into position, if it meets the right catalyst, which we'll talk about later, it transforms into the ultimate killer. The hydroxyl radical, that's an OH with a dot.
The sources describe this one in absolutely terrifying terms. They call it the most reactive species known to biology. Not one of the most, the most.
It is the undisputed serial killer of the cellular world. The hydroxyl radical is terrifying because it has absolutely zero discrimination. Scientists say it reacts at the diffusion limit.
Okay, break that down for me. Diffusion limit. What does that mean in practice?
It means it reacts with the very first thing it physically bumps into. It doesn't look around for a specific target. It doesn't float for a while until it finds a weakness. If it is created next to a DNA molecule, it destroys the DNA instantly. If it's next to a protein, it shreds the protein. The reaction happens in nanoseconds. There's no travel time.
And because it acts that fast, I'm guessing you can't stop it.
You cannot stop it. This is the crucial point. You cannot build an enzyme to catch a hydroxyl radical. An enzyme works a lock and key. It takes time to find its substrate and click into place. By the time an enzyme could even register that a hydroxyl radical is there, the damage is already done. The house is already burned down.
So once it's formed, there is no defense.
The only defense is to prevent it from forming in the first place. Once the pin is pulled on that grenade, you can't put it back.
That is genuinely scary. There are a few others in the gallery too. Singlet oxygen is on the list.
Singlet oxygen. This one is a bit different. It's not about adding an electron. Remember the spin restriction, the parallel spin issue that keeps us safe.
Yes, the back-to-back handshake. The safety lock.
Singlet oxygen happens when you pour energy into the molecule, usually from light, like UV radiation, and you physically flip the spin of one of those outer electrons.
So now instead of both being clockwise, one is clockwise and one is counterclockwise.
Exactly. Now they're opposite. The safety lock is broken, and suddenly oxygen can react with things directly, snatching whole pairs of electrons. But not by adding an electron, simply by absorbing energy. This is a big reason sunlight damages your eyes and skin. The UV light is constantly creating singlet oxygen in your tissues.
And finally, the last one here is nitric oxide. I thought this was a good guy. Doesn't it lower your blood pressure or something?
It does. It's a critical signaling molecule. It relaxes your blood vessels, but it has a dark side. It is a double agent. If nitric oxide, which is itself a radical, meets superoxide, that gateway drug we met earlier, they combine.
A team up.
A very toxic team. They react together instantly to form something called peroxynitrite.
Peroxynitrite. Sounds bad.
It is nasty. It's a powerful oxidant that wreaks havoc on proteins, especially ones with sulfur. It's a classic example of two things that might be manageable on their own, becoming catastrophic when they get together.
Okay, so we have this whole gang. We have the thug superoxide, the Trojan horse peroxide, the serial killer, hydroxyl, and the double agent nitric oxide. My big question is, where are they coming from? Is this just from, car exhaust and x-rays and pollution?
Well, all of those things certainly add to the load. They absolutely make it worse. But here is the really uncomfortable truth. The call is coming from inside the house.
Inside the house.
The vast, overwhelming majority of the oxidative stress you face every second of your life comes from your own body doing exactly what it's supposed to do to keep you alive.
So this brings us to the inside job.
And for that, let's talk about the mitochondria.
The powerhouse of the cell.
Yeah.
I think that is the only sentence I remember verbatim from 9th grade biology class.
It's the one thing everyone remembers, and for good reason. But let's look at how that power plant actually works. It's not a clean-burning natural gas plant. It's more like a leaky old coal furnace.
Okay.
It burns food using oxygen to make ATP, which is the energy currency of the cell. It does this using a very clever assembly line called the electron transport chain.
An assembly line. I can picture that.
Imagine a bucket brigade. High-energy electrons stripped from your food are passed from one protein to another down a wire, essentially. At each step, they squeeze out a little bit of energy, and at the very end of the line, the exhaust, these now low-energy electrons, are safely dumped onto an oxygen molecule to make harmless water, H2O.
That's the ideal scenario.
That is the ideal, perfect textbook scenario. In this perfect world, oxygen sits patiently at the end of the line, catches 4 electrons, becomes 2 molecules of water, and we all go home happy. But the system isn't perfect. It leaks.
It leaks electrons.
It leaks electrons. The sources estimate that about 1% to 4% of the oxygen you breathe doesn't make it to the end of the line. It picks up a stray electron early, it falls off the conveyor belt, and what does it become?
Superoxide?
Superoxide.
1 to 4%. I have to say it sounds small.
It sounds small, but do the math. Think about how much oxygen you consume in a day, a kilogram, more. Now think about a lifetime. 4% of that total volume is a massive, staggering amount of toxic waste being generated right inside your most sensitive and important machinery.
So my own power plant is just constantly spewing radioactive waste directly into my living room.
Constantly. This mitochondrial leak is the primary source of endogenous, meaning internal oxidative stress. It is literally the price of breathing. The harder your engine runs, the more you exercise, the more you eat, the more leaks you have.
Is this why some people say a high metabolism is actually bad for longevity? That old theory?
It's a major component of that theory, yes. The rate of living theory. Small animals like shrews have incredibly fast heart rates and metabolisms. They burn hot, leak a lot of ROS, and they die in a year or 2. A giant tortoise burns incredibly slow, leaks less, and can live for 150 years. It's an oversimplification, of course, but the thermodynamic principle holds.
But wait, the notes also say that sometimes the body makes these things on purpose.
Yes. This is where the plot thickens considerably. Our immune system, specifically the white blood cells called phagocytes, uses ROS as a primary weapon.
How so?
Imagine a white blood cell, like a macrophage, hunting a bacteria. It catches it and swallows it whole. But how does it kill it?
I always just assumed it digests it.
It does, but it tenderizes the meat first. The cell undergoes what's called a respiratory burst. It has an enzyme on its surface that deliberately pumps massive amounts of superoxide and biological bleach hypochlorous acid into the little containment chamber with the bacteria.
It gas chambers bacteria with free radicals.
Effectively, yes. It dissolves the bacteria from the outside in using the same toxic chemistry we spend the rest of our lives trying to avoid. It is literal chemical warfare.
But chemical weapons are notoriously hard to control. They tend to drift.
Exactly. Friendly fire is inevitable. If you have a state of chronic inflammation, say an old knee injury that's always sore, or an autoimmune disease, those phagocytes are firing that bleach and those radicals into your own tissues day after day, year after year. This is why chronic inflammation is so tightly linked to cancer and aging. It's the collateral damage from your own army.
There is one other internal source the notes emphasize, an enzyme called xanthine oxidase. This one seemed really specific to, like, heart attacks and strokes.
Yes, this is the ischemia-reperfusion paradox, and it's one of the cruelest jokes in all of biology.
Okay, set the scene for me.
Someone has a heart attack. A clot blocks an artery. The heart muscle downstream is starved of oxygen. That's ischemia. The cells are dying, but they aren't dead yet. They are panicking.
And during this panic, their internal chemistry changes.
Drastically. A normal, safe enzyme called xanthine dehydrogenase gets chopped up by other panic-induced enzymes, and it turns into xanthine oxidase. And it just sits there, building up in the tissue, waiting.
Waiting for what?
Waiting for oxygen. Then the doctors rush in, they put in a stent, they clear the blockage, blood rushes back into the starved tissue.
Reperfusion. The oxygen returns. The day is saved.
You would think the tissue would say, "Thank you, we're saved." But instead, that sudden rush of fresh oxygen hits all that xanthine oxidase that built up, and boom, the enzyme uses that oxygen to generate a massive, catastrophic explosion of superoxide and hydrogen peroxide.
So the cure, the return of oxygen, actually causes the damage.
Paradoxically, a huge amount of the tissue death from a heart attack or stroke happens after the blood flow is restored. It's a second wave of destruction caused by the sudden availability of oxygen to a compromised system.
That is absolutely devastating.
It is. It's a major area of research, how to reintroduce oxygen slowly or with antioxidants to prevent this reperfusion injury.
We should briefly touch on the external sources too, just so people know what to avoid. We mentioned radiation.
Radiation is the classic external source. Ionizing radiation, X-rays. Gamma rays acts like a microscopic bullet. It zips through your body, hits a water molecule, and physically blasts it apart. This is called radiolysis. It splits H2O directly into a hydroxyl radical and a hydrogen atom.
And since we know hydroxyl radicals kill DNA instantly.
That is the primary mechanism by which radiation causes cancer and radiation sickness. It's not the energy itself that does most of the damage, it's the chemical storm of hydroxyl radicals it creates in the water of your cells.
And then there's specific toxins. The outline mentions paraquat. What's that?
Paraquat is a particularly nasty herbicide. It's incredibly toxic to humans. It works by hijacking the electron transport chain in plants.
The same one we have in our mitochondria.
The very same one. Paraquat steps into that assembly line, steals an electron, hands it off to an oxygen molecule to make superoxide, and then immediately goes back to steal another one.
So it's a perpetual motion machine for creating free radicals.
It is a catalytic generator of superoxide. It turns the the human's own energy system into a suicide machine. That's why paraquat poisoning is so often fatal and has no real antidote. It turns your own metabolism violently against you.
Okay, so we are surrounded. We have leaks from the inside, toxins from the outside, and friendly fire from our own immune system. But I really want to talk about the catalyst, because looking at the chemistry in the notes, it seems like there's one specific ingredient that turns this bad situation into a catastrophic one. And it's something I actually took a supplement for this morning, iron.
Iron, Fe, the heavy metal of life. We absolutely cannot live without it. It carries oxygen in our blood. It's a key part of those mitochondrial enzymes. But if it gets loose, it is one of the most toxic things in the body.
Why is free iron so dangerous?
It comes back to our rogues gallery. Remember hydrogen peroxide, the Trojan horse?
The one that can travel anywhere in the cell.
Exactly. On its own, hydrogen peroxide is slow to react. It's dangerous, but it's somewhat manageable. But if it bumps into a loose iron atom...
The Fenton reaction.
This is one of the most famous and most destructive equations in all of pathology. The Fenton reaction. Iron, in its ferrous state, Fu2 plus Lin, reacts instantly with hydrogen peroxide. The iron hands over an electron, which splits the peroxide molecule apart, and in the process creates the hydroxyl radical.
The serial killer.
The serial killer. Iron is the trigger that turns the stealthy Trojan horse into an immediate, indiscriminate massacre. And the worst part is that the iron isn't even consumed. It can be recycled by superoxide, that's the Haber-Weiss reaction, and go on to do it again and again. A single atom of free iron can churn out thousands of hydroxyl radicals.
This explains so much. It explains why the body is so completely paranoid about iron storage.
Obsessively paranoid. If you look at human biology, you will almost never find a free iron atom floating around. It is always handcuffed. In the blood, it's locked inside a protein called transferrin. Inside the cells, it's locked in a big, hollow protein cage called ferritin.
Because if it breaks out of jail...
If it breaks out, it starts lighting fires everywhere. If you have a crush injury where cells burst and all their iron spills out, or a genetic disease like hemochromatosis where your body absorbs too much iron, your ferritin cages get full. They overflow. The free iron spills out. It meets the steady stream of hydrogen peroxide leaking from your mitochondria. And suddenly, your tissues just start to dissolve from the inside out.
Dissolve.
Effectively, yes. It just destroys the structural integrity of the cell on a massive scale.
Which brings us to the actual damage. Damage. What does this look like at a molecular level? If I could shrink down and watch a hydroxyl radical attack my cell, what would I actually see?
You would see a landscape of absolute destruction. We have three main targets that get hit the hardest. Lipids, which are fats, proteins, and, of course, DNA. Let's start with the lipids.
This is lipid peroxidation, right?
Exactly. Think of a stick of butter you leave out on the counter in the sun. After a day or two, it turns a deeper yellow and it starts to smell sour and funky. It goes rancid.
Okay, that's oxidation.
That is lipid peroxidation in your butter. Now, your cell membranes, the walls that hold all your cells together and keep the insides in and the outside out, are made of a lipid bilayer, specifically polyunsaturated fatty acids.
And the radicals love those.
They absolutely love the double bonds in those fats. So a radical, like a hydroxyl radical, comes along and rips a hydrogen atom off the fat. This creates a carbon-centered radical on the fat molecule itself. Now, the fat molecule is the radical.
It's been infected.
It has. Then that fat radical reacts with an oxygen molecule to form a peroxyl radical. And here is the truly scary part. This peroxyl radical now attacks the neighboring fat molecule right next to it, stealing its hydrogen to stabilize itself.
So it passes the hot potato down the line.
It creates a domino effect. One single hit from one hydroxyl radical can initiate a chain reaction that unzips the entire membrane. It can damage hundreds or thousands of lipid molecules. It turns the cell wall from this flexible, selective barrier into a leaky, broken sieve. Everything starts leaking out.
And the notes mention that this process produces some nasty byproducts. Aldehydes. What are those?
Yes. When the fat molecule gets attacked and broken down, it eventually snaps into smaller, toxic pieces. And these include very reactive aldehydes like MBA, malondialdehyde, and 4-HNE, 4-hydroxynonol.
Those sound like industrial solvents, not something that should be in my body.
They act like them. See, the hydroxyl radical lives for a nanosecond. It hits the membrane and it's gone. But these aldehydes, they're much more stable. They can detach from the broken membrane, float through the cell fluid, and act as secondary messengers of death.
That's the zombie analogy from the outline. The radical is the initial bite, but the zombie, the aldehyde, wanders off to bite other people.
Exactly. It wanders off and finds a protein across the cell, or even gets into the nucleus and binds to your DNA. It spreads the damage far away from the original site of the injury. It propagates the fire.
Speaking of proteins, how do they handle this kind of attack?
Not well at all. Proteins are these incredibly precise, folded machines. They're like origami. Their shape is everything. Oxidation acts like rust on the gears of these machines. It attacks specific amino acids. Cysteine and methionine are very vulnerable because they have sulfur, which oxidizes easily.
And this creates carbonyl groups. I saw that term.
Right, carbonylation. It's a chemical stamp that gets put on the protein that basically says this protein is broken. When a protein gets carbonylated, it usually loses its function and unfolds. Enzymes stop working. Structural proteins become brittle.
And can the cell fix them? Or get rid of them?
Sometimes. The cell has a recycling center called the proteasome. It's like a molecular paper shredder that chews up bad proteins. But here's the problem. Sometimes the proteins get so damaged and cross-linked, especially when they get gunked up with those rancid fats we just talked about, that the recycling machinery can't chew them up.
It's like trying to put a bowling ball through a paper shredder.
Exactly. It jams the machine, and this indigestible junk just starts to accumulate inside the cell. It clumps together into a material called lipofuscin.
Lipofuscin. That's the age pigment, right?
It is. If you look at the back of the hand of an elderly person and you see those brown spots, the liver spots,
Yeah.
that is quite literally a visible bag of lipofuscin inside their skin cells. You are looking at a lifetime's accumulation of oxidative trash that the cell couldn't get rid of.
That's incredibly visceral. It's literally looking at the garbage dump of a cell's history, right there on the skin.
The lysosomes, which are the cell's stomach, get clogged with this stuff. And eventually the cell just stops functioning well because it's full of this inert, undigestible trash. This is a major, major component of the aging process at the cellular level.
So let me just recap this absolute horror show. We have our own mitochondria leaking toxic waste 24/7. We have loose iron atoms acting as a lighter fluid to turn it into a chemical bomb. We have our cell membranes going rancid and leaky. We have our proteins rusting and clogging up the internal trash compactors.
It's a grim picture, I'll admit.
It raises a very serious question. Why aren't we dead? I mean, really, why don't we just dissolve into a puddle of goo by the time we're 5 years old?
Because of the defense. That brings us to our last bit. Why we don't just dissolve. We have focused very heavily on the strategy of attack today because that's what the source material Druga Course Lanu details so well in this specific section. But implied in all of this is an equally sophisticated defense system.
The antioxidants.
Exactly. We are not defenseless. We have a whole army. We have enzymes like superoxide dismutase, or SOD, that stand guard right at the mitochondria to catch superoxide the instant it's made. We have catalase that takes hydrogen peroxide and instantly breaks it down into harmless water and oxygen before it can find any iron. We have a molecule called glutathione, which acts like a sacrificial shield, taking the hit so our proteins don't have to.
So it's a constant war going on inside of us.
It is a dynamic balance. Health is when the defense is, on average, matching the attack. Disease and aging are what happen when the attack starts to overwhelm the defense. That's the state we call oxidative stress.
But the sources mention a really interesting twist here. We shouldn't just want to eliminate all ROS, right? I mean, it's not a good idea for me to go inject myself with pure antioxidants.
Correct. And this is a very modern understanding that has changed medicine. If you completely eliminated all free radicals from your body, you would actually die or develop cancer very quickly.
Why? I thought they were the bad guys, full stop.
Because the cell, in its wisdom, has co-opted them for signaling. At very low levels, A puff of hydrogen peroxide is not a weapon, it's a messenger. It's a smoke signal. It tells the cell, hey, metabolism's running a bit hot. Maybe it's time to make some more antioxidant enzymes. Or, hey, it's time for us to divide.
And if things get really bad,
Yeah.
if the damage is too much,
It sends the ultimate signal, apoptosis, programmed cell suicide.
which sounds bad, but is actually a critical safety feature.
It's absolutely crucial. If a cell has its DNA damaged so badly that it might become cancerous, you want that cell to commit suicide for the good of the organism. ROS signals are one of the main triggers for that self-destruct sequence. If you block that signal with mega doses of antioxidants, you might actually be allowing a precancerous cell to survive and multiply.
So the second phase of oxygen is even more complex than we thought. It's not just a killer, it's also a stern teacher. It keeps the cells in line.
Precisely. It's about balance, not elimination. It's a concept called hormesis. A little bit of stress actually makes you stronger. Too much kills you.
Wow. This has been a journey. We've gone from the discovery of oxygen in the 1700s to the quantum spin that keeps us safe, all the way to the electron leaks in our power plants, the iron triggers, and the literal rusting of our cellular machinery.
It really changes how you view a simple breath of fresh air, doesn't it?
It completely does. It feels like a deal with the devil.
That is the ultimate synthesis here. We all complex life on Earth chose the high-energy lifestyle. Aerobic metabolism gives us, something like 18 times more energy per glucose molecule than anaerobic metabolism. It allowed for brains, for consciousness, for movement, for civilization.
But the cost.
The cost is that we built our house inside a slow-burning furnace. The damage is inevitable. It's a law of thermodynamics. We spend our entire lives repairing it as best we can. But eventually, the entropy wins, the rust accumulates, the candle burns out.
It brings us right back to Priestley's candle. We burn bright, but we burn out.
And that leads to a final provocative thought to leave you with. We know that the hydroxyl radical reacts instantly. We know we can't stop it with an enzyme once it forms. We know our mitochondria leak these precursors constantly every second of every day.
Right.
So is aging simply the inevitable tuition fee for being an oxygen-breathing life form? Are we just destined to rust?
Or, to flip it around, is the very thing that slowly kills us. The only reason we're complex enough to sit here and care about dying in the first place.
Deep thoughts for a deep dive. Next time you take a deep breath, just take a second to appreciate the delicate, violent chemistry that stops you from bursting into flames.
Indeed. Stay balanced, everyone. Thanks for listening. We'll catch you on the next one.